You know, in engineering, we usually start by asking, what should the system do when something happens? What's the right action? What is the right response? But lately, I've been wondering about something different. What if the real test of intelligence isn't just knowing what to do, but knowing when it's better to wait, when it's smarter not to act at all? Today, healthcare monitoring systems like those in ICUs are designed with one overriding principle: detect any deviation, alert immediately. And the result, if you ask, studies show that between 80 and 90% of alarms in critical care settings are either false alarms or real signals that do not require urgent action. It's almost hard to believe. Just imagine almost everything that the staff hears doesn't actually need them to respond. In engineering, we simply call this noise, the meaningless signals that should be filtered out. But when the system doesn't filter it, the people do. If you've ever been by the bedside of a loved one in the hospital, you know the feeling. You see the monitor connected to your parent or your child, and suddenly the screen flashes red. The alarm sounds. Your heart races. You call the nurse, urgent and afraid. They come, they check, and they silence the alarm. It's not important, they say. It happens again and again. And over time, even you, the worried relative, start to ignore the beeps because when everything is urgent, nothing feels urgent anymore. You see, it's not that the systems are broken. They were designed with a different fear in mind. In healthcare system design, the greatest sin isn't raising a false alarm, it's missing a real one. And so the philosophy became simple. If there is even a small chance something bad is happening, better to sound the alarm, wake up the ICU, even if it's nothing, rather than miss the one silent heart stopping in the night. Historically, healthcare systems maximized sensitivity, catch every possible event, even if it meant drowning in false positives. But today, with better sensing, better data, better understanding of patterns, we have the chance to rethink that balance, to not only maximize sensitivity, but to improve specificity, filtering out the noise, and to raise precision, ensuring that when a system signals, it's because something truly demands our response. But when we flood the system with noise, something dangerous starts to happen. The people it's meant to protect, the caregivers, the therapists, the nurses start tuning it out. In some ICUs, the flood becomes so unbearable that nurses and therapists, driven crazy by constant alarms, start turning down the volume of monitors. They silence the alarms, not because they don't care, not because they don't know the risks, but because the human brain simply wasn't built to survive a never-ending storm of false warnings. And you have to wonder, when we build systems that force people to choose between drowning and hearing the truth, what exactly are we designing? But we could change that, not someday, today, because today's technology gives us tools we never had before. machine learning, real-time sensor fusion, confidence modeling across multiple signals. For the first time, we can improve not just sensitivity, but specificity. Catch the true events, ignore the noise, and raise precision so that when a system signals, it truly matters. Sometimes improving precision isn't just about smarter thresholds. It's about giving the system more ways to perceive the world, adding more sensors, adding more context. It's like giving the system new senses, not just feeling one heartbeat, not just seeing a blood pressure reading, but sensing the flow of the body, hearing the quiet shifts behind the obvious signs. The more senses a system has, the more wisely it can understand the difference between noise and a real call for action. Of course, we have to ask, can embedded systems today carry that weight? These aren't massive servers. They're tiny devices, often running with just tens or hundreds of kilobytes of memory, powered by milliwatts. Maybe the answer isn't brute force, maybe it's elegance. Small, careful logic, embedded intelligence, designed not to rush, but to understand. Maybe the answer isn't building one giant heavy brain. Maybe it's in many small, wise systems working together in harmony. Tiny nodes, each lightweight, each specialized, synchronized perfectly. We already see this kind of harmony in the cars we drive. Dozens of small embedded controllers managing braking, steering, stability, all working together, not chaotically, but in harmony. Maybe that's the future for healthcare too. When we design systems that work in harmony, when we let small pieces listen to each other, something changes. The system becomes more than a sum of its parts. It becomes something alive, something wise. And maybe that's the real question we've been circling around all along. At the start, I asked, what if the real intelligence in a system isn't in how fast it acts, but in how wisely it waits? Think about the people you trust most, the mentors, the surgeons, the pilots. They rarely react instantly to every bump, every scare. They listen carefully, they wait, and they act only when action is truly needed. Maybe we should expect the same wisdom from the systems we build. Maybe embedded systems of the future won't just be machines that react. Maybe they will be living systems, harmonized, patient, watching over us, not flooding us with noise, but signaling carefully, thoughtfully when it truly matters. Because real intelligence, whether in a person or in a system, isn't just in what it can do, it's in knowing when not to act.